Swayam Prabha. Digital India. Educated India.
Hello students, so today we are continuing the discussion for the future cities and the ecology, and today's topic is instrumented study. So in this we will be covering instrumented urban ecosystem, cities as living laboratories, why instrumented urban ecosystem are necessary, what gets instrumented, the domains of measurement, instrumentation as a feedback loop, and we will specially have a section on the digital twins as the core tool and urban digital twin. Case examples as usual we'll be discussing and future scope of instrumented urban ecosystem. So let us start with the instrumented urban ecosystem, which is an urban socio-ecological system, and in this blue-green and built components are systematically equipped with networked sensors, data acquisition devices and communication technologies so that it can enable continuous high resolution observation of environmental conditions, ecological processes and ecosystem service provision for research, planning and governance. In practice, this idea of instrumented urban ecosystem combines the conventional notion of urban ecosystems like cities and towns, including built structures, transport networks, parks, gardens, and other blue-green spaces, with city-scale sensing and urban observatory infrastructures that fuse data from Internet of Things devices, remote sensing, and citizen-generated measurements. Cities as living lab. Cities function as living labs by serving as real-world test beds for urban experiments, innovations, and solutions to complex challenges like sustainability, mobility, and climate resilience. The concept is very similar like the urban sandbox. Urban living labs are defined as real life urban environments where diverse stakeholders, including governments, businesses, researchers, citizens, and academia, they co-create, test, and prototype innovative solutions to address wicked urban problems. This concept positions cities as living laboratories for experimentations, learning loops, and scaling feasible interventions, often at neighborhood or city scales. And we can see its examples in practice in many countries, many cities, like in Amsterdam. There is Amsterdam Institute of Advanced Metropolitan Solution, and their urban living labs are testing sustainable mobility and circular economy solutions across the city ecosystem. In Barcelona, Smart City project uses data and citizen engagements as a living lab for open data, social innovation, and smart services. In Copenhagen, we have seen the climate is getting the priority. Climate Adaptation Living Lab, they experiment with adaptation solutions in real neighborhoods. There are also other such living labs. Why this instrumented urban ecosystem are important? Urban ecosystems are no longer stable systems that can be planned once and that is good enough. And that will help the city governance to manage through the static regulations. The complete changes has happened in the scenario, climate variability, infrastructure aging, and rapid urbanization. All these things together are demanding continuous observation and learning the new normal. Instrumentation will enable the cities to detect stress before the system fails, evaluate real performance rather than assumed benefits, and it will help in transition from reactive to adaptive governance. Traditional master plans are based on infrequent surveys and fixed assumptions. Instrumented urban ecosystems rely on continuous data streams that enable recalibration of decisions in near real time. Planning becomes an iterative control process, not a one time blueprint. So it is replacing snapshot assessments, proxy based indicators, assumption driven planning, and what it can bring. The urban ecosystem performance, it varies across seasons, extreme events, long term degradation, or recovery cycles. So, this instrumentation can introduce temporal intelligence, allowing planners to identify trends, thresholds, and early warning signals. So, let us see what can get instrumented. Instrumentation focuses on system performance, not physical form. Key domains include hydrological response like for rainfall, stream flow, water level, infiltration, runoff measurement. Flood peaks, retention volumes in NBS, rain gardens, permeable pavements, their performance also can be measured. The second domain is the thermal behavior, surface and microclimate temperature, air surface temperature, humidity, UTCI. They are the measuring index. Urban heat island mitigation by green infrastructure. This can be monitored once we are having this thermal behavior properly instrumented and measured. Ecological functioning is the third domain. We can measure the vegetation response recovery, NDVI, chlorophyll, phenology, soil nutrients, to monitor the biodiversity signals like acoustics, cameras. We can use post disturbances recovery. Next domain will be the infrastructure stress and efficiency, which can be measured like drainage or road load, utility pressure, vibration. We can measure also the energy or water use, NBS performance. The fifth dimension, which can be instrumented, that is human exposure and service reliability performance. For that, we can go for instrumentation like personal pollutant, heat, noise exposure, park usage, flood warning, service metrics, etc. can be measured. Instrumentation creates a closed loop systems in urban ecosystem, transforming raw sensor data into actionable intelligence, and that continuously refines ecological management and urban resilience. So the core cycle, the closed loop, will be sensing, analytics, response, and learning, and again continuously going back to the sensing. The sensing, the data acquisition, let's say the hydrology, rainfall gauges, soil moisture probes, stream level sensors, drainage flow meters. For thermal, air ground temperature grades, humidity, radiative flux sensors. For ecological one, we can use the NDVI, cameras, SAP flow meters, acoustic diversity monitors. For infrastructure, we can measure through vibration, instrumentation, pressure, energy or water flow sensors. Next stage of this is the analytics. Once you gather through the sensors those data, now you try to generate your insight on the scenario. So machine learning anomaly detection flags the deviations from the baselines. Digital twins can simulate intervention outcomes. Predictive models can focus cascade effects. And now we can go for the next stage using these two steps: response and adaptive action. Automated action like smart irrigation, floodgates, cooling misters. So these are actually being actuated once the data sensed are being analyzed, and now trigger is being created. Similarly, semi-automated can actually, operator alerts can start the targeted intervention. Strategic policy dashboards for long-term planning. And the next stage is the learning, which represents the system evolution. Continuous model recalibration from outcomes. Return of investment analysis guides scaling decision. Climate scenario testing builds future resilience. And we will come to one very specific instrumentation, advanced instrumentation tool, I will say, that is the digital twin. A digital twin in urban systems context is a dynamic virtual replica of a city or district or infrastructure that integrates real-time data from the IoT sensors, GIS and other sources to mirror physical reality and simulate the scenarios and support predictive decision making. Digital twins continuously synchronize with their physical counterparts through bidirectional data flow, enabling what if modeling for urban planning, operations, and resilience. Unlike static 3D models, they incorporate AIML for behavioral emulation and scenario testing. The key components of digital twins that include a physical asset that an enterprise aims to monitor, analyze, or simulate in a virtual environment. A virtual model that acts as a digital representation of the real world object or system. Data sources such as sensors or Internet of Things devices that continuously record relevant metrics like temperature, pressure, or motion. A data pipeline that transmits sensor data to the virtual model, keeping it synchronized with its associated physical asset in real time. A feedback loop that sends insights or control signals from the digital twin back to the physical assets to optimize performance, efficiency, and decision making, then only it is actually having a very strong implementation. An analytics engine often powered by machine learning or artificial intelligence that can detect data patterns, simulate future scenarios, perform predictive analysis, and assist with asset tracking. Visualization interfaces and dashboards that enable teams to interact with a 2D or 3D representation of assets or systems. And this visualization this interface is very important component, because this is something which makes the scientist group or technologist group who are working behind the scene, they can actually have a discussion with the decision makers. So how the digital twin works, you can see here physical asset is here. This is the physical asset, and you are creating a digital twin, the virtual model. Data storage and processes are there. Analytics and AI will help to assess the data, and visualization and interface will be created. And sensors are connectivity that IoT is always there, which is helping the digital twin to keep on working and bringing the real-time assessment. So the insight optimization action, engineering docs are there, GIS is there, maintenance system, business network, financial systems. It can really have so many different wings to bringing together. We can discuss this very specific use of this digital twin in the urban areas. That is an urban digital twin, UDT, which relies on a number of layers of data that build on top of each other. Like you have the data layer, you have the information layer, you have the knowledge layers. So these are the number of layers, and everywhere you are having different type of data. First direct data somewhere, and then that direct data is being utilized to develop the other data. So this layering in information about the terrain, buildings, infrastructure, mobility, and IoT of devices, that is very helpful for the urban setup. The digital twin uses the data generated in the virtual smart city layer. I will be discussing this smart city layer as well, which brings the information to the IoT, and GIS is there, the data sources which you are creating. You have also the data platform 3D city model, integrated urban model, and then the PSS, SDSS, and BIM and city information modeling. So you have different layers, and accordingly from the data it goes to the information, then you use the algorithms, and then you monitor and control those information so that it's an interactive platform. And then through the collaboration of different data sets, you can actually measure and monitor the city. This information is feedback through the layers of the model where it can be implemented in the physical world. The PSS stands for the Planning Support System, SDSS stands for the Spatial Decision Support System, CIM stands for the City Information Model, BIM Building Information Model. So many different layers are there, so many different information you can generate, and depending on your usage, you actually use the relevant data set. So the stakeholders can be many in a city. It can be governance bodies, citizens, asset owners, managers, and academic sites. There can be many different levels also: service level, simulation level, digital modeling, data acquisition, and the physical world. We actually start from the physical world and we go towards the simulation side. So city, and we can get many different type of information: mobility, then the gazettes, then the sewage, and all these services, electrical pollution information, meteorological information. And then data acquisition can happen through the sensors, digital modeling, city information model, mobility simulation, many different type of simulation platforms you create on that. Then the actual simulation is being done, and we can see the application of machine learning and the logics, 3D simulation, etc. And we see who is going to use what. If someone, the urban planning asset manager, the mobility roads and infra, water supply, so it can be different infra centric, or in combination it can be the managers as well. So urban digital twin can be actually very strong interlinked modules to help many people together. We will bring some examples how different cities are actually working on it, and we one by one we'll be discussing them. For Helsinki is the virtual Helsinki, for Sydney sustainability twin, for Aachen, transport digital twin, for Incheon from South Korea, multifunction city twin. Uppsala in Sweden have developed the green growth district twin, and the Pretoria, South Africa is using the twin for their waste management. Helsinki in Finland is a citizen-centric planning tool for carbon neutral Helsinki by 2035. They are saying it's Helsinki 3D plus. 3D city model with real-time sensor data, traffic, air quality, energy are the inputs. Public AR/VR interface for project visualization is being used. Scenario simulation. Once you get the data, then you start acting on it. So scenario is getting simulated. Solar potential, wind patterns, development impacts are being done. How it works: data from 100 plus sources continuously fits the BIM GIS models, while AI simultaneously simulates planning scenarios. So citizen can access the platform via web or mobile interfaces to comment and vote on the proposals, creating feedback loops that directly inform city decision making processes. In the case of Sydney, we will find the data-driven sustainability and safety planning. For that, the twin has been utilized. Input data set, you can see air quality, traffic volume incidents, the weather, GHG emissions, and the crime incidents. So different frequency of this data collection is there, and different methods are there, whether it's a point data, whether it is a area data that has been mentioned, and the data since when. That is very important for a city. If they have a good set of data, obviously the prediction will be always better. What are the features of this particular sustainability twin? We can find the integration of weather, crime, emissions, traffic data sets, and machine learning powered risk prediction like crash hotspots, sustainability scores, etc. Suburb level analytics dashboard, that is also are part of this twin. How it works: heterogeneous data streams flow into machine learning models that generate predictive indices for planners. City officials then prioritize interventions at high risk intersections and low sustainability suburbs based on these quantified risk profiles. So that's the way they directly take advantage of the data feed. Like they have done it like this: you just go for any year, for any particular region, and you can find different information. So ranking of suburbs and descending order of transportation related emissions in 2018, that has been represented here. Actual emission values can be seen by clicking on a suburb in the map. The digital twin allows visualizing the data set according to various categories and across different years. And this visualization is a very strong quality of the twin, which is actually connecting people with the digital tools easily. Next example is from Germany, Aachen. This is also related to the transport. Integrated mobility management is the target. LiDAR-based 3D model of 970-kilometer road network, real-time traffic simulation like vehicles, cyclists, pedestrians, etc. All info is there. Cross-departmental API integration. How it works: sensor feeds from cameras and inductive loops continuously update traffic flow simulations that predict congestion patterns. The system then generates dynamic signal timing recommendations and long term mobility planning strategies for city departments. In continuation, we can see these two nice images. The first one talks about the prototype of Aachen digital twin above the road, providing a visual representation of road infrastructure of city of Aachen. And the second one shows the prototype of showing the road infrastructure below the surface, which is crucial for long-term maintenance planning and optimizing the life cycle of city assets. So whatever you create, whether below ground or above ground, every information you can really bring together so that the decision making and maintaining the facilities are easy. Incheon, South Korea, multifunction city twin. The purpose is unified municipal operation. It covers 6 domains: fire response, traffic, sanitation, facilities, disaster management, urban planning. So it's a huge platform, you can see. Real-time dashboard for 500 plus turf and GIS plus Internet of Things integration. How it works: 30 departments continuously feed live operational data into centralized analytics that generate automated alerts and optimization recommendation. Fire track routing, for example, achieves 10% faster response times through real-time path optimization. Incheon, we can see that they decided to build a 3D base map for its digital twin, and the digital twin looks like this, the screenshot. It decided to build a 3D base map for its digital twin, creating comprehensive city model that supports integrated urban operations across fire response, traffic management, sanitation, facilities maintenance, operation and maintenance, disaster preparedness and planning. In the fifth case, we will find a very good example from the eco-centric ideas of Green Growth District, Uppsala, Sweden. Sustainable district development planning is the purpose, and the feature of this twin is detailed 3D model of 33,000 housing units of the 50,000 residents. Biodiversity, carbon, energy simulations are part of it. Stakeholder collaboration platform, it works like that. How it works: BIM data combines with environmental models to assess the development scenario, which impacts iteratively, continuously changing. Stakeholders refine proposals through visualized carbon and biodiversity outcomes, progressively aligning with the climate positive 2050 targets of the city. So, Uppsala created a detailed digital twin to enhance sustainability, just like we have seen the case of Incheon. And this Rosendal district digital twin enables comprehensive impact assessment of proposed 33,000 unit development, ensuring alignment with aggressive climate targets through continuous scenario simulation and stakeholder collaboration. Pretoria, South Africa, waste management twin is a very interesting one again. Smart waste collection optimization, citizens are reporting via app, GPS route optimization for containers, litter hotspot mapping. 820 sites are identified. How it works? User reports integrate with bin fill sensors to generate the dynamic collection routes that complete 3-day mapping cycles across the city. Fuel consumption and emissions decrease through continuously optimized logistics planning and waste generation simulations that provide information about waste flow, low capacity areas, optimal container locations, and it looks like this. The containers, they are having those sensors, so they are always being tracked. Optimized collection routes are proposed to reduce fuel use and emissions. A control dashboard has been developed which includes stakeholder system requirements and display 11 indicators on 3 maps. Now we convinced that instrumented initiatives are helping the cities for not only sustainability but also to take care of its services as well as ecology. Future scope of instrumented urban ecosystem. Instrumented urban ecosystem will evolve into artificial intelligence of things driven, self regulating, cyber physical living systems that autonomously optimize ecosystem services while adapting to climate extremes and population pressure. So, that is the future we are expecting. This AIoT driven urban brains, they will edge AI processes which trillions of sensors are reading to predict the ecosystem failures and autonomously deploy the interventions like microbial remediation, adaptive irrigation, etc. Cities become smarter eco-cities with 95% reduction in maintenance response time. So these are the positive parts of these interventions. Living digital twins, quantum enhanced twins simulate inter-urban metabolism, testing synthetic ecologies and human behavior at population scale. Enables ecological what if planning for rise in temperature of 2 degrees Celsius scenario. Biodigital symbiosis, neuromorphic sensors embedded in engineered organisms, they are creating self-healing ecosystems. Buildings photosynthesize via algal facades, which we discussed in last class. Streets host microbial carbon sinks, all autonomously regulated. So, today we have discussed a lot on this instrumented urban ecosystem and tried to understand the future of it. These are the list of references. Thank you.